And also, and maybe some of you know me from, I've been a professor at Tokyo Tech for a long time.
I'll give you forward.
Oh yeah, thank you. I built a series of machines like the Tsubame machines, which was, the first probably GPU machine to be in the top 500 and the first to achieve petascale in Japan. And the most recent GPU machine I built last year was ABCI, which is AI, now the fastest supercomputer in dedicated to AI. I think officially it has like 4,300 volts, but became the fastest by running the ImageNet, ILS-VRC 2012 dataset training in 75 seconds, which beat the Google's record of 2 minutes. So we're the fastest now. And also Riken, our center, which used to be called AICS, we basically house and run the K computer, which was the fastest supercomputer in the world at one time. And then I was recruited to become a director here, and then they renamed the center to be RCCS, Riken Center for Computational Science. And then, so just to show you that, we just don't, run the K computer or develop, Post-K. This single slide, just to show you that we're doing a whole bunch of research on high-end computational science, and both computer science, which is science of computing, and the more traditional computational science, which is science by computing. And also looking at interaction with other parts of Riken and others, because we have huge accelerators and all these facilities like the OE labs. And we're a very big science, and we're Max Planck. So we work with lots of other scientists to try to drive the next generation computing. In particular, we have started the project on post-Moore computing in the 2027, 28 timeframe, and also looking at stuff like quantum. But today I'll focus on the Post-K and the ARM64fx chip. That actually we started the first consideration Post-K back in 2009, 10 years ago, way back. Officially, the Post-K project kind of started in 2012, the precursor project, and then in 2014 it was officially inaugurated. So it's been 5 years, and I've been involved in various functions. And this is just a single takeaway slide. So if you forget everything else, this is a take-home message. So Fujitsu and Riken, we've been again designing this machine for the last 5 years, 7 years, or 10 years, depending on the level of from early to some mid-consideration to actual detailed design. But the resulting processor, the A64fx, which supports the ARM v8.2 SV extension, is a 7 nanometer 48 or 52 cores actually, or CPU. But compared to other processors, which are not HPC optimized, but rather optimized for things like web workloads, this is a processor that's totally HPC optimized. So it has a terabyte per second memory bandwidth, has an on-die network, which is effectively a 400 gigabit network integrated onto the die. It's about 3 teraflops, so it's about Cascade Lake performance in terms of flops, but it has much higher bandwidth. And also it has various AI supports like FP16 and 8. But it's still a general purpose CPU, it's not a GPU. So it can run, runs Red Hat, for example, right out of the box. Enterprise right out of the box. It runs Windows too. And it can run Word if we want. It's extremely energy efficient. So on some of the benchmarks, we've seen about order of magnitude better per watt performance on things like CFD application on a real chip. This is not simulated on a real chip. And I'll show some of the numbers. And these are real numbers on a real chip, which is production chip. And then we take the chip and we build the largest supercomputer in the world. So I can't disclose the exact number of nodes yet. Probably in a few months we'll be able to. But the machine it'll be the largest machine ever built. It'll have more than 150,000 nodes, which is bigger than in terms of number of nodes, it'll be bigger than the previous biggest machine, which was IBM Livermore Sequoia, which has 132,000 nodes. Physically, of course, it's a much bigger machine. But most importantly is not so much the flops. We all know that for real HPC application, it's really the bandwidth that counts. That's Seymour Cray, basically, it's the bandwidth. Right? So the machine has, theoretically, has more than 150 petabytes per second bandwidth, which is about order of magnitude bigger than any other machine in the world. Slightly less, but somewhere in that range for real applications. And the 60 torus network, which is an improved version of a TOFU network on K, basically gives you about 60 petabits of injection bandwidth total, which, by the way, to put this in context, is about 10 times bigger than all the IDC traffic. There are about several hundred hyperscaler data centers in the world. But the traffic there internally is about, in 21, Cisco expects it's about 50 petabits per second. So we have about 10 times that capacity. And we have about 25 to 30 petabyte NVMe storage. And the I/O fabric, not the main fabric, but I/O fabric is InfiniBand. And but it has 10,000 endpoints. So it's actually bigger than Summit. The I/O fabric is bigger than Summit. So it'll be the first exascale machine, effectively. Well, not in flops. We won't hit exascale flops, but then that's not our goal. Our goal is to achieve exascale performance in real applications. And in fact, we project that many of the follow-on machines and that will claim exaflop will be by and large equivalent or less or whatever. Well, at least on parity with this machine's on real applications. But this machine will come out in 2020. So, maybe a couple years earlier than the other machines. So this is the machine we're building right now, and we'll probably see it by the end of this year. The first batch of installations. So that's the takeaway, and the rest are the details. Okay, and so to put this in more of a high-level context, so we think it's really a game changer because K computer was sort of good, was very large, but and it had achieved lots of scientific achievements. But at the end of the day, the technology employed there, the best technology employed there was the fabric. The fabric was wonderful. This had the best fabric in the world, but the processor wasn't all that great. We did a lot of benchmarking of, taking like the Intel Xeon of the same era, and then did a comparative benchmark, and by and large, the Spark FX8 chip that was in K performed by and large the same as the Xeon, on a chip-to-chip basis. So the goal of Post-K was to achieve 2 orders of magnitude speed up, 100 times speed up on some of our key application benchmarks compared to K. And we'll achieve that. But we'll achieve that, but not only by just making a continuum of machine, but to have lots of innovative features. And this is actually the die picture of the production chip. So you see the central chip, and you see the HBM2 alongside. So it has a much higher performance because of extreme high bandwidth in the chip compared to any of the mainstream processors, by far, by several factors. It's very green too. I can't disclose the exact numbers, but on a per socket, for any workload, be it compute bound or memory bandwidth bound, the entire node, it's a single socket node, but the entire node, including the memory, the CPU memory, the optical interconnects, everything is below 200 watts. So they're very green. And all the, GPU or superior to GPU green performance. But still, like I said, it's ARM. So, it's part of ARM ecosystem. So just like, as we enrich the ARM ecosystem, And all the open source stuff, according to studies of various people, including work at Sandia, work at Bristol, and so forth, and work by us, demonstrated that we have a very credible ecosystem, and not to mention that we get everything from the embedded world. And over the course of time, there are several architectural changes made, new workloads like big data, and of course AI came up. So several design changes were made along the line to support these artificial intelligence functions like FP16 and Int8 and 16, and also accumulation, and high precision accumulations and so forth. So the A64fx processor in a nutshell, it's a 48-core processor, 7 nanometer. It's a brand new core design, doesn't use any of the ARM IP except for the architectural license. That is, we can take the instruction set, but everything internally within the chip is designed, was co-designed with Fujitsu and us. So doesn't use any, it's not a derivative of any of the ARM core design. So integer performance is sort of, probably around Haswell class. So it's not as good as Skylake or Cascade Lake, which, for integer performance, Xeon flies. But it's pretty good. And as you see here, it not only has the 4 quadrants, this is a single chip. It's not like a chiplet architecture like the AMD, but it's a single die. But it has 4 quadrants, but it's all cache coherent. And also, in this coherent domain, we have the TOFU network and also the PCIe embedded in the chip. So it's on a CPU, but also but on the other hand, as the architecture was optimized for HPC. The chip was not designed to run things like web workloads. I mean, it can do it, but it'll be a waste. So we have SV 512-bit vector extensions, if in fact it's double pumped. This has a sort of a scratchpad-like memory capability called sector cache, which is a carryover from the K design. So it's not exact local memory, but it allows you to segment the cache to achieve this localized cache effect, which is utilized quite frequently with GPUs for optimization. Has HBM2 on-package memory, terabyte per second. So we've maintained the bytes per flop to be about 0.4, 0.5, which is about the same ratio as K. So all the application ran on K just ports straightforwardly onto this machine. And there are other memory enhancement features like barrier, intra-chip barrier synchronization, has things like memory coalescing and all those features you may want to optimize your memory hierarchy. So, that's the A64fx processor in a nutshell. So in terms of the timeline, of course, like I said, we've been developing this stuff for several years. But the most recent timeline, so the May 2018, the A0 chip came out, tested it, almost bug-free. Of course, a few bugs, but nothing critical. It booted the Red Hat right out of the box, which was quite amazing. The first quarter, of course, the bugs were fixed. 2019, we have the B0 chip, which has become the production chip. And of course, we had to go through all the procedures, get the national projects, so all the government approvals and contract signing, which we had to do. But now we signed the contract, so we're full steam ahead with producing a machine. In August, we'll end the K computer operations, take a few months to do the revamp of the data center, bump it up to 40 megawatts. And the fourth quarter, the installation will start. Of course, there may be some early access program. If you ask Fujitsu, maybe they'll give you they can give you access sometime during the fall of 19. And the first half, the pre-production operation will start. We'll have the full machine. And then hopefully within 2020, maybe slip into 21. 2020, late 2020, we'll go to full acceptance and full operation of the machine. This 150,000+ node machine. So, and Fujitsu will come out with the commercial version announcements, as well as the possibilities for other system vendors, system OEMs to adopt the chip. Because, after all, it's just an ARM chip. There's nothing special about this chip except for the tofu, too. So it can go into any other form factor. It can go into the cloud. And so this was achieved with extensive co-design because we had the K and other supercomputers. And the single factor for this machine was to co-design with our key applications in HPC. No web workloads, anything like that. So, and this was started way back in 2009. And of course, we got a lot better once we had the K computer, which in 2011, so we knew what the workloads were, how the workloads are. But we went through this meticulous phases, and I won't go into all the details of how, all the science, how the science teams were, it was a really a national effort. And then basically, we came up with the 9 co-design applications. And then we set on to do the architectural investigation as to how to optimize a chip. And some of the co-design apps were very complicated and for example, ran on a K. Of course, people wanted this to be 50 to 100 times faster. So something like complex, multiple, not simple molecular dynamics like this, but multiple molecules interacting within a cell, or like membranes. So several billion cells interacting dynamically, or sub-kilometer global climate simulation, or even this can be applied to ultra high resolution regional forecast. But something like this is very important to predict global warming, which I believe will happen, but some people do not. But, and also things like very intricate heart simulation. I think there was an example, but this is really much more sophisticated. It's not just the dynamics of structural. It also simulates the blood vessels and the blood flow, and also the electrical pulse signals and everything. So, and in very detailed fashion, each cell. In fact, they model each cell as not just a structural membrane, but they model each cell individually as the functional unit. So this is, but of course they want exascale performance out of this to be able to do what if kind of diagnosis, like what happens when you have, when the blood vessel clogs, what effect will have on the rest of the heart. So there are applications like that. And then we went through the simulation. We had several vehicles to do this. And Fujitsu has several vehicles to do this. We wrote our simulator. We did lots of architectural investigations, like how to determining the SV vector length, whether 512 bits times 2 is better, or like 1024 bit is better. There are many parameters which you can. Okay, but but the end result is this. It's 7 nanometer chip, 52 cores, has 32 gigabytes of HBM2 with a terabyte per second performance, has a PCIe. Well, this chip, this is a generation 1 chip, so it's sort of optimized to be embedded into Post-K. Although, this can be general purpose. Maybe there will be follow-ons to this chip later on. But I can't tell you about that. But largely, it's the double precision performance is about 3 teraflops, and you got the fairly reasonable clock frequency. It's got 4 what I call CMGs, 4 memory groups, which has 13 cores, and it's connected by this network on chip. But these are not separate chips. This is one single chip, and also these CMGs are all cache coherent. So, but the reason we have this quadrants is the fact that within the quadrant, these cores are all crossbar connected. So you've got full cache coherent bandwidth. In fact, so skip this. So again, this is more of a cartoon view of the CMG. So you got the crossbar connection between all the cores. We don't have meshes or within the CMG or rings. Rings connect the CMG, but within the CMG, it's all crossbar. So, and also with L2 cache, And then we don't have L3 because HBM2 is quite fast. So the total system bandwidth of the chip at the L1 level is about 11 terabytes per second. And since this is a crossbar that connects all the cores and also the L2 cache, the injection bandwidth here is about half of this. So you get about, but we still get about, we still get about 1/3. So we get about 3.6 terabytes per second into within the crossbar. And then we got a terabyte per second in the memory. And then there are various memory enhancement features. In the interest of time, I'll skip. If you're interested, a lot of these details have been presented at Hot Chips 2018. It's also on our webpage, at Riken's webpage. So, look for ARM64fx. Google that, you'll find it. It's got power monitor, which was the API which we developed at Livermore and also Sandia. But this is the first chip to implement the power monitor interface, the standard interface. Also has power control to, for example, reduce the number of execution units, just aside from the clock frequency, voltage control, but you can do explicit power gating of the ALUs to reduce power for like memory bandwidth bound operations. And this actually has a significant effect. For memory-bound operation, this drops the power consumption by something like 40 watts or so. So, and also, I skipped over, but has a RAS feature that's mainframe class, because Fujitsu has been making these mainframes. So they put in mainframe class RAS, just as they did for K. So, and when you have a 150,000 node machine, you need mainframe class RAS to run the entire machine. So, very reliable, and we have experienced that with K, and we expect that to carry over for Post-K. So, there aren't too many performance results that are disclosable yet, although we do have the numbers, but we can't tell you everything yet. This is one baseline. So the DGEM is about 2.5 teraflops. Actually, it's a little better now. The stream triad is about 840 gigabytes per second. It's about 8 times faster than on a chip-to-chip basis compared to x86 architectures. These are some of the representative code, although it doesn't really say what they are, just the category: CFD, atmospheric, seismic, and these are like convolutional operators. And the baseline is the Spark A64fx, which is a previous generation Fujitsu chip. So then you ask, what's that? Oops. So by comparison, I'm sorry for all the Japanese. I didn't have time to translate, but this is comparing the FX100, which was the baseline chip, to Haswell. So you can see that these are pretty much equal across, for example, so NAS parallel benchmark. But this is a two-chip. These are two-socket machines. So on a comparative basis, on a node-to-node basis, about the same. On a chip-to-chip basis, so about 6 times faster compared to Haswell. And then if you look at the some of the numbers, some of the baseline numbers, so compare it to Knights Landing or Skylake, you'll see that the memory bandwidth is about 8 times bigger compared to Skylake, about the same as NVIDIA Volta. And also, DGEM efficiency is extremely high. It's like 94%. So if you're interested in like Gaussian, this is very high. And impact efficiency also very high, nearly 90%. And for give flop per watt for impact is probably a little better than NVIDIA Volta. But what about for other applications like CFD? So this is we have some like WRF results and stuff like that, but we can't disclose it yet. There's a very simple CFD benchmark like Himeno, which is a direct numerical solver with CFD. So, but it's a benchmark. It's a one data point. So this is the number for the Xeon Platinum 8168, but this is a dual socket, and this is the FX100, so about the same. But Post-K is about 4 times faster, and even faster than the Volta or the XXOR, which is NEC's vector chip. And the power for this, again, is less than 200 watts. Whereas, like on this platform, it's about 500 to 600 watts. So on Himeno, this will be about power efficiency of the chip is about an order of magnitude better than Skylake. I mean, measured. Okay. Well, but your mileage may vary. For some of the workloads, Skylake is fantastic. It'll beat this chip. Depends on your workload. So this is how it's packaged. We have a dual socket. It looks like a dual socket node, but actually it's not. There's 2 nodes in a package, but it's a board about this big. The reason it's small is that it doesn't have a DIMM. It's totally directly water-cooled. Has some of the optical interconnects and has 384 nodes in the rack. And also, actually, the TOFU network is embedded with the both copper and AOC interconnect directly from the board, actually from the chip in the board. Now, the 6-dimensional, well, those of you who do not know what TOFU is, a 6-dimensional folded torus. And and like I said, the HCA is not connected via PCIe through the I/O bus, but directly connected to the network on chip. So it can do, not only has very high bandwidth, but also can do some other tricks like do direct cache injection, also have global addressable memory. So for running anything like PGAS and one-sided communication, or even accelerating MPI, it's the low latency of this chip is really low because you can inject directly into the L2 cache of some of the other chip. It's not cache coherent across. Right? So the latency across machines about directly the neighboring nodes about 0.5 microseconds. And the bandwidth is about 40 gigabytes per second for the entire injection bandwidth, which is about 93% efficiency, which is equivalent to having about 400 gigabit network per node. So skip over D. Well, so this is how it scales. So in total, and we'll have like first layers, we'll have about 25 to 30 petabyte NVMe. Second layer has hundreds of petabytes of luster-based GFS enhanced by Fujitsu. So in total, it have 150,000 nodes, or about 8 million cores, high-performance ARM cores. Like I said, 150 petabytes of memory bandwidth, and 60 petabits of TOFU, 10,000 endpoints, 400 racks, and the machine power is fairly high. It's very power efficient, but when you have 150,000 nodes, we still need a 40 megawatt facility. The PUE will be below 1.1, but we'll see. But the NRE for the machine, I think, paid off even before the commercialization aspect, because this will be equivalent to having something like a 15 to 30 million core machine. And at market prices you see today, the machine would have cost several times more had we bought the off-the-shelf components and built the machine. Rather, by developing and spending a few $100 million on NRE for the ARM chip, even for this machine, is already beneficial to reduce the cost and make it realistic. Not to mention that, of course, it'll probably have very strong commercial impact. So we're prepping our data center. This is you can't see it, but this is our building, hosting our offices in the K computer. This is the cogeneration plant on all the cooling for the current machine. The 3 stories high has a cogeneration plant and all the cooling tower inside. And this is a new cooling facility we just built, but it's still empty inside. But this will have about 20 megawatts worth of cooling. So in total, we have a 40 megawatt, both 40 megawatt plus power supply plus, and also the cooling capability in Kobe. And forgot the software, but it's all standard. But we'll, of course, enhance it for SVE, but also we'll support containers. We'll support a lot of AI workloads because we believe this, and we'll also support a whole bunch of all these familiar applications we would think will run very fast on this machine. And finally, we are working on with ARM and other partners to enhance the deep learning capabilities, and we believe this machine will be very good at it. Well, maybe on a chip basis, the dedicated GPUs will probably win over because of some of the arithmetic functions, specializations like voltage tensor cores, which is fantastic. But on standard workloads on a per watt basis, those chips still should be fairly competitive because of specialized instructions and units. And also, when you try to scale deep learning, which we're doing as research, I'm doing personally research, you need very fast interconnect to do, for example, due to the aggregation of the activations. So it becomes a network bound, quickly becomes network bound problem as we scale. But our goal is to try to scale deep learning to 100,000 nodes on this machine and make it the fastest AI machine in the world as well, not just with HPC. Okay, so that's it. And by the way, we still have a few days to name the machine, because Post-K is just a code name. And I'm sick and tired of calling it Post-K, because I know we're not going to call it Post-K officially, and the naming contest is on.
Not special K.
There's been several thousand applications of varieties of very innovative names, but if you're interested, yeah, you can submit your naming application now. If you win, you get a prize. Okay, that's it. Thanks very much.